the most important part, because the first part, I think most of you probably knew that already. This is, as I said before, really the heart of everything that happens in cement. And clearly I can't tell you every single detail, and clearly there are details we still don't know. So what I'm going to try and talk about this morning, just to give you a feel for things, is that in terms of hydration, first of all, what are these new solids that form? You know, we said that the anhydrous phases, which are this C3S, C2S, C3A, etc., they react with water to form new solids. And first of all, we need to talk about what are these solids. Then we'll talk a little bit about the time scale on which this occurs and how this overall gives us our microstructure. And finally, we'll come back to this changes in solid volume, which is what we looked at very, very simply over here. And we'll look at this in a little bit more level of sophistication. And clearly, in terms of the projects in this transcend, what we're interested in is the final microstructure. So, composition of solids. Well, this is the hydration process. So I already told you this. This is our starting point. These are cement grains in resin. So you see here's our different phases. Here's our C3S, here's our aluminate phase, here's our ferrite phase, etc. And these are going to transform to a final microstructure like this. So, okay, the gray levels change in order that we can see these hydrates. So this is a cement grain here, which is partially reacted, and you see this layer of product around it, and you see all this product in between. This is basically what we're going to talk about. The overall reactions, first of all, we can divide them between the silicates and the aluminates. And if we look at the silicate reaction, you'll see that both C3S and C2S react to give us this compound, which is called CSH. Now, CSH is written like this deliberately. Okay, so it's C-S-H. And please don't write it without the hyphens, because that's wrong, okay? Because the reason for having the hyphens there is because the stoichiometry, that's to say the ratio of calcium to silicon, the amount of water within the structure can change. So there isn't a precise stoichiometry for this phase. And you'll also see that these are not stoichiometrically balanced equations. Okay? But clearly, if we have the same amount of calcium to silicon here and here, this means we'll end up with a lot more calcium hydroxide here. And we're going to talk about half this session about this compound CSH. And why are we going to talk about half the session on CSH? Firstly, because it forms about half of the final microstructure. So it is the most important phase by a long way. But secondly, because it's not a nicely crystalline, well-organized material, its structure is still unknown on several levels. And its structure is also responsible for a lot of the complexity of the interaction of concrete with water. So all these projects in Transcend about interaction of concrete with water, the CSH is a very important compound in that. But at the same time, we don't want to be too obsessed with CSH, because when we look at some of the newer cementitious materials we can imagine to make in the future, these can be materials without CSH in them. Okay? So CSH is complex, it's important, but we need to see exactly what can be attributed to the CSH and what are more general things. Then we have the reactions of the aluminate and, to a certain extent, ferrite phase. These give these compounds, which we call these horrible names, AFT and AFM. Okay? Now, I'll say a bit more detail what these mean, but basically this AF here means that it can either have aluminium in the structure or it can have iron in the structure. Okay, so they tend to be interchangeable, although in practice we find that because we have such a high pH in cement paste, the iron tends not to enter these compounds to any great extent. And T here means tri, and the M here means mono. But we'll explain all that in a bit more detail later on. So now let's go from the cement powder. And the cement powder, as I told you before, is about 70% C3S. In this example, 15% C2S, 8% C3A, 7% ferrite. That would be pretty typical proportions for a Portland cement. And this reacts with water. There's an increase in volume. That's proportional to the increase in volume here. And at the end, this says for a 14 months paste. You can assume that's kind of a mature state of things. You see at the end of this 14 months, we have about half of this compound CSH. We have some anhydrous material that hasn't reacted. We have calcium hydroxide, which is a very important phase. We have these two AFM, AFT phases down here, and we have porosity. Okay? So porosity is always very important. I'm not going to talk in detail about porosity today because that's the subject of the lectures on Wednesday morning. So basically, the C3S and the C2S form a CSH and calcium hydroxide. The aluminate and ferrite phases form this AFT, AFM. So now let's look at these products of the calcium silicate reaction, calcium hydroxide, CSH. Calcium hydroxide is a nicely crystalline material. We know its crystal structure extremely well. If there's a lot of free space, it will form these nice crystals like that. That's very misleading because in practice, it has to form in the pore space. So it will form as these kind of areas here. You see these pale gray areas, this is calcium hydroxide. And you see it's just filling up the space that's left over by the other products. The other thing that's confusing, as I said, the same thing has lots of different names. So we can call it calcium hydroxide. In English, it should have an I instead of a Y, sorry. We can call it hydrated lime. It's called Portlandite. And it can be written as CaOH2 or CH in cement chemistry notation. Okay? And all of these tend to be used interchangeably. The other thing is this calcium silicate hydrate. Here we can see what it looks like on a fracture surface in the scanning electron microscope. And we're going to come back and we're going to look at this in a lot more detail. Now, you'll read most places that it's amorphous. I think nowadays most people will agree that that's not really well expressing the state of things. I think it's much more correct to say that it's nanocrystalline because it does have a very definite structure on the atomistic level. So we're now going to look at CSH. As I said, we're going to spend about the next half hour talking about CSH. And first of all, we're going to look at the structure on the atomic level. Then we're going to look at the meso level, which is, how those atomic packets, how those nanocrystalline packets are arranged. And finally, the microstructure morphology, as we can see in scanning electron microscopy. Now, if you read a lot of textbooks, they often carry on like CSH is this kind of big mystery. I think it's not a big mystery, and particularly it's not a big mystery now compared with 30 years ago. 30 years ago, we didn't really have a very good idea of its structure. Now we do. But even before that time, it is a definite phase with a systematic behavior. And this is what I want to show here. Here you see solubility data from a large number of people ranging over, I think this study was done in the 1940s even, to studies done 5 or 10 years ago. So the important thing here is that all of these studies show the same thing. So CSH hasn't changed. It had a behavior. It's always got that behavior. And whoever does the measurements can see the same thing. What we see here is on this axis, we have the calcium to silicon ratio. This is something very important. I said at the beginning that we wrote it C-S-H because the stoichiometry could change. And this is what we can see here. We can see that the ratio of calcium to silicon changes over this range from about 1 to 1.5 or so. The calcium to silicon ratio changes according to the concentration of calcium and other ions, but mainly calcium, this is by far the most important, in solution. So in this graph here, the CSH range is this range here. Okay? At this point here, we also start to form calcium hydroxide, and at this point here, we start to form silica gel. So people have we produce CSH in cement paste. We can also make it by mixing together different solutions. So this is what I mean here, that generally when you mix together different solutions, you get a precipitation. You can produce calcium silicate hydrate in the range 0.8 to 1.5. As we'll go on to discuss, in cement paste, this often tends to have a higher calcium to silicon ratio. And I'll explain the reasons why this is somewhat higher. Now, for a long time, people have realized that CSH has certain similarities to this natural mineral tobamorite. Okay, so you can find natural calcium silicate hydrates, the most famous of which is this mineral tobamorite, because it was found on the island of Tobermory in Scotland. And here you see X-ray diffraction data. Here you see solid-state nuclear magnetic resonance data. If we look at the X-ray diffraction here, you can see that there's some reflections in the CSH which are in the same as the tobamorite, but we've lost most of the reflections. We've lost most of the reflections because it's more disorganized. Okay? And this is a synthetic CSH made in the laboratory with calcium to silicon ratio 1.1. If we actually take the CSH that forms in cement paste, we don't even hardly see these reflections. We may get a kind of bump here and a bump here, okay, because it's even more disorganized. Nevertheless, this gives us an idea that there's certain similarities between these two things. And over here on the nuclear magnetic resonance, you see these peaks are labeled Q1, Q2. I'll explain in a bit more detail what these mean in a minute. But Q2 means a silicon that is attached to two other silicons. So it's in the middle of a chain. Q1 means a silicon that's attached to one other silicon. So this means at the end of a chain. And we see here that in the tobamorite, we've just really got Q2. So this means we've got infinite chains that go on and on. And the big difference between tobamorite and the synthetic CSHs, you see that we go from chains where everything is in the middle of chains, i.e. the chains don't have any ends, to where we practically only have ends of chains. Okay? So we just have little dimers of silicate. Now, this is the basic structure of tobamorite. It's shown schematically to make it simpler. The three components of this are, first of all, we have layers. The layers are layers of calcium and oxygen. So you have calcium and oxygen forming sheets. And then onto these sheets, we have chains of silicates. Okay? So silicon, this red atom, is always bonded to 4 oxygen atoms, and those 4 oxygen atoms are arranged in a tetrahedra. So these little green things are meant to be tetrahedra of silicates, SiO4. Okay? And this is where we can see about the chains and about sharing. So depending on how many other silicates these are linked to, you see in these chains, each of these tetrahedra is linked to 2 others. So these would all be Q2 groups. And then finally, we see that between these layers, we've got water molecules. So that's the 3 basic elements of tobamorite structure and also of CSH structure. It's a sheet structure of calcium oxide sheets with silicate chains on it. And here's some electron micrographs. So I think this one here is tobermorite, which is quite well organized. This is CSH. You can see there's still the idea of layers, but they're more disorganized. So solid-state nuclear magnetic resonance is really the tool that has enabled us to well understand CSH. This has all been done in the last 30 years. It's well established that depending on the number of silicate groups the silicate is attached to, this determines the position of the resonance peak. And so we start from what we call Q0 groups, which are present in C3s. This is silicate, which is attached to no other silicates. We go down to chains, and chains have ends, which are Q1 groups, and middle bits, which are Q2 groups. If you go on to sheets, as you have in clays, you have Q3 groups. And if you go on to a continuous network like quartz, silica fume, you have Q4 groups. So sorry, these numbers got a little bit detached. But we'll see that in CSH, we basically are concerned with chains. So this shows a typical spectrum from a concrete. And the different peaks, you see this is quite a noisy spectra. This can be deconvoluted into these peaks. And then these peaks can be associated with different groups. So these groups down here are the Q0 groups coming from the cement that's not reacted. These different peaks here, and you can see it's really kind of quite difficult to get this quantitatively, but you can pick out these Q2 groups, which are here. These, you can even pick out the Q2 groups, which bridge these two little dimers, as opposed to this Q2 group here. They have slightly different shifts. And then you have a Q1 group, which is the end of a chain here. So by putting all this together for different preparations and everything, we've really managed to be well established at an atomistic level what's the structure of CSH. Is that clear to everybody? Some people are looking a little bit puzzled, I can see. Yes?
Yeah. Okay, I've never worked with solid-state NMR. I only know this NMR, which is used for organic chemistry analysis. But I find it very, let's say, brave to see the peaks there. I would just say that's a broad peak, or maybe a multiplet, but nothing more.
No, I mean, you know, this is obviously a controversial issue. And I think the important thing that's been done is that, you know, this is the most complicated situation you can get, where you've got everything in together. And it sort of builds on a lot of knowledge that has come from making synthetic CSHs. When you have a synthetic composition without any other things in, then it's much clearer. So, you know, they do that first, and then they go through here. But you're quite right. I mean, you have to take all of this quantification with a little bit of a pinch of salt, because clearly there will be errors involved. Any other questions there? But you see, in this one, they even claim to be able to differentiate CSH from the sand. You know, sand and quartz are very well crystalline, so they have this nice sharp peak. And then we have this material called silica fume, which is a glass structure which has a very broad streak peak. Okay, so that's just the same that's just showing you these different positions again. So this is now the CSH structure drawn out in terms of atoms. You see here's our calcium oxide sheet, and here are the silicate chains on this sheet. And you can also see that we have this very interesting arrangement of the chains that was already visible in this diagram back here, that we have what is called this dry Ketten structure. Okay, so it goes 1, 2, 3, 1, 2, 3, 1, 2, 3. You see two of them are attached to the sheet, and one of them is what's called a bridging site. And it's these bridging site ones that are most often missing. So this is then how we go from tobermorite structure, which has a calcium-silicon ratio of about 0.83, I think, if I remember rightly, to CSH, which has a calcium-silicon ratio which is much higher, getting towards 1.7 or even 2. So this is the starting point. This is if we have complete chains, and these silicates up here, they have a corner which is not joined to anything else. This then has to be balanced by either a hydrogen or, as we'll see later, a calcium. So this is our starting point, calcium-silica ratio 0.7. And the first thing we can do is to have these bridging sites missing. Okay? And if we remove all these bridging sites, we can get to a ratio of about 1 or so. After a certain point, we can't go any further by just removing these bridging sites, and then we can continue to change the calcium-silicon ratio by replacing 2 hydrogens for 1 calcium. Okay? So this is the next stage to increase the calcium-silicon ratio, and in this way we can go to a CSH ratio of about 1.3 or so, 1.2, 1.3. And then the question is, well, you know, we're still below the calcium-silicon ratio of CSH. And how can we get further? Well, there's a lot of debate about that, but I think probably the most people would agree that, in fact, what we have is probably some regions that are like calcium hydroxide. Well, what does that mean? It basically means you've got this sheet and you've got no silicates on it, because that is the calcium hydroxide structure. And it's all these kind of missing tetrahedra, missing bits of silicate chain, which mean you have a disordered structure of CSH as opposed to the well-ordered structure of tobamorite. And this is a model that was published recently in PNAS, where they tried to put in the different distributions of silicate chains and come up with a model for what they call CSH. There's a lot of controversy about this, if this is right, or, you know, have they chosen the right distribution. That's, you know, an ongoing debate, but the important point here is that you can see that as you start to remove these silicates, these layers become disorganized. They become kind of rough. And this is why you don't see a good X-ray diffraction pattern. Also, because of this defects, it means that we actually can have water molecules between these layers. And this becomes very important as regards to what's really happening in terms of interaction with water with CSH. So, going about it the other way around, I said, you know, we talked about having missing groups in our silicate chains. Well, in fact, what happens over time is that we start with these little dimers, and then slowly, so over time, the dimers tend to join together to form pentamers, and then octamers, and then 13 groups here. This is a very slow process, so for a typical Portland cement, the average chain length, even after a year, will typically only be 2 point something. So it will be mainly dimers with just a few pentamers, for example. And as I'm going to talk about after lunch, this is one of the main things that changes when we put in supplementary cementitious materials. We tend to increase the chain length. Further complications. I mean, you know, you thought it was complicated already, but it hasn't finished yet, is that we can also have some of these bridging sites with aluminium in rather than silicon. Okay, so aluminium is a fairly similar atom to silicon. It can form tetrahedral groups like this. Of course, these will then have a charge on them because the aluminium has a lower charge than the silicon. And if we look at these kind of analyses taken in the scanning electron microscope of cement paste, I'll explain how we do these kind of plots later. But you can see this kind of cluster of analyses here. These represent the calcium silicate hydrate, and they have a quite definite amount of alumina attached, which is typically an alumina to calcium ratio of about 0.05. And interestingly, you know, all Portland cement without additions seems to have roughly the same amount of alumina in. So that's really the atomistic structure. And I mean, what you really need to keep in your head is this kind of idea of a layered structure, layers based on calcium oxide sheets, this idea about the silicate chains, the complexity of these silicate chains starting to lengthen, the incorporation of aluminium, and finally the idea that there's water between these sheets. Any more questions? Any questions on that? Okay, so now we go on. This part, the atomistic structure, I think this is now pretty well established, pretty high level of agreement. This next part, the Muzo structure, is probably the area in which there's most controversy and most uncertainty about CSH structure. And unfortunately, this is exactly the level that really is important for this whole area of water transport. So questions you would think would be very simple, like how much water is there in the CSH structure at a given relative humidity, we don't well know the answers because of this uncertainty about the Muzo structure. Now, where do we start from? Well, what's the evidence we have? Well, as I've said before, we know there's no long-range order. So we have a certain disorganization in this CSH structure. We have also, since a long time, since there was Powers who was working in the 1940s and 50s, we have this idea that there's an intrinsic porosity. Now, this is a very important and rather bizarre notion. Powers did all his work by drying. Okay, so he sort of had this cement paste, he kept it at a certain relative humidity for a very long time, and then said, okay, how much weight have I lost? How much water have I lost? And by doing things in this way, he said, this CSH gel has an intrinsic porosity of about 26 to 28%, which is quite a high number. I mean, you've got this solid forming, and you're saying, you know, a quarter of it's space. Now, I think you really have to think that's an upper limit, because what's certainly clear is that the way he was doing his experiments, not only are you losing sort of the water between the particles, which we're going to talk about in a minute, but we're also losing water even for within the layers. We talked sort of back here where we had this model about the fact you could have water in the layers. It's quite clear that in Powers' experiment, he was drying so severely, water was coming out of these layers. But nevertheless, you have this point that as you form more and more CSH, you get more and more of these pores in a small region. And in the last few decades, there's been an awful lot of work with scattering experiments. Go away. With scattering experiments, which have indicated that there's a kind of characteristic size of this intrinsic porosity or whatever that's maybe in the region of 4 to 5 nanometers. So this was a starting point for various models. And then over the years, people have put forward lots of different models for this CSH structure. So this shows 4 of the most commonly quoted. And really what I want you to focus on, with the exception of this one down here, which I think most people would now totally disregard, is not the differences but the similarities between these ones. Okay? So, I mean, I always find it rather weird that these two at the top, one is by Powers and one is by Feldman and Sereda, they had such rows about them that they were not on speaking terms, because they were claiming these were totally different models. But, I mean, if you draw them like this, I think, you know, most people can see these look more similar than they look different. As I'll come on to say, I think the essential point of difference is whether we have little separate blobs, you know, little separate bricks of CSH which don't really have a connectivity together, or whether we have things where the sheets tend to extend from one particle to the other. And that's still largely the area of controversy today. We've got these nanocrystalline regions, so you see these regions here which are well structured. These are nanocrystalline regions which have the atomistic structure that I showed you earlier. So this is the idea of the sheets, etc. But are they separate, like in this model and in this model, or are they more joined together? So this is another piece of work where people claim that these particles are separate. This is an atomic force micrograph taken after 4 hours, and it's claimed to show calcium silicate hydrate, little bricks here, growing on the surface of C3S. From that, we have this model, which was published about 4 or 5 years ago in Nature Materials, which shows this idea of these blocks. Now, I'm going to spend a bit more time on this model because from the point of view of water, what is nice in this model is to see the different states of water. So here we have this idea of these little colloidal particles. Within these little colloidal particles, we have our sheets of calcium oxide and silicate, and then between these sheets we have water. So we have water in this interlayer space, which you see here is regarded as physically bound. Now, it is to a certain extent physically bound, but you can also, by drying very severely or heating up to even quite moderate temperatures, like 50 degrees or so, you can start to lose some of this water in this space. We then on the surface of these particles, okay, which is assumed to be like a monolayer or 2 layers, or we don't exactly know. And finally, we have what we call the water in these nanopores. Okay. So this is kind of, I think, quite a good conceptual model for CSH gel, as it's often called. Said earlier, I think the main point of controversy depends on whether these little nanocrystalline areas are joined together or not. And clearly that is going to have an important effect on a lot of properties. But nevertheless, the existence of these different sorts of water with no clear division between them. Because if you do a drying experiment, you're going to sort of progressively lose, first of all, this water that's in the bigger pores and then get to this layer here. But at the same time, you're going to start to be losing water from this interlayer. So it's very, very difficult experimentally, and this is the reason why there's so much uncertainty on the structure, to cleanly divide these different types of water. And when we come to this, when we come to be concerned with things like transport, this is also why CSH makes life very problematic. So this is the kind of idea of a granular structure with disconnected regions. This is hotly debated because if we look in the transmission electron micrograph, where we have quite a high level of resolution, I'm sorry, this is a kind of, we're getting down to a nanometer resolution here, we don't see these little grains. And we really would expect to see them now in the transmission electron microscope. Instead, we see these kind of filmy structures which seem to extend over quite long distances. Okay? And this would probably be more compatible with this kind of model like this, where we have sheets that extend from one region where they're well organized to the other. So this would kind of support the idea that these kind of little nanocrystalline regions are actually joined together in the same way you have in a polymer structure. Those of you who have studied polymer structures, the structure of semicrystalline polymers, will be familiar with this idea of regions where the polymer chains are well organized and then the polymer chains go to another region. So this is really the big controversy which is still not resolved about CSH. And to complicate things further, the work we started in Nanocem at the University of Surrey, we started this about 6 or 7 years ago, and we started to use this technique of Proton Nmr. Now, earlier I showed you Silicate NMR, that's NMR done in the solid state. This is in the liquid state, and what we're looking at here is the mobility of water. Okay, so the protons are present on the water molecules, and the relaxation time, these axes here are what's called relaxation times. I'm not going to go into the details, but these relaxation times depend on how quickly a water molecule hits the edge of a pore. So when you've got free water, you have a very long relaxation time because the water is moving around, it never hits the edges. As you go to smaller and smaller pores, so we're going to smaller and smaller pores down here, we have shorter and shorter relaxation time. And this experiment, where we've got two different relaxation times, T1 and T2, and I'm not going to worry about the details of this. This is just a way of being able to better discriminate different pore sizes, and also, interestingly, to be able to study exchange between different pore sizes. So when we started to apply this technique to CSH, we came up with a very surprising result. That was that instead of having one type of pore associated with the CSH, it seemed there were two types of pore associated with the CSH. So before we did this work, the conventional idea... Sorry, this microphone is going on and off all the time. Hello? Okay. So before we did this experiment, the conventional wisdom was there was one kind of pore in this CSH. And this kind of pore in the CSH had this about 5 nanometer size. And then from this Proton Nmr, we start to see there's two kind of pores in the CSH. So this kind of really throws the cat amongst the pigeons, because this doesn't really correspond to any of the existing models of CSH. And there's another complication, because this exchange thing here says that the time for water to go from one type of pore to the other type of pore is actually quite long. Okay? Now, something being quite long either says these two types of pore have to be quite a long distance apart, or there has to be some other reason why the exchange between the two of them is quite long. And we couldn't think of any sensible theory as to why two types of pore should be quite large distances apart. So the model we now really think is probably closest to the truth is that one of these types of pores is water in the interlayer, and the other type is then these pockets between these different nanocrystalline regions. And the reason you have a quite long exchange time is this is obviously within a semi-crystalline structure, so there's quite a long exchange time for water to come in and out between the sheets. This is our current state of thinking. As I say, this is work in progress, and several of the students here are going to continue, Agatha and Nick and etc. are going to continue to work on this problem. So just to summarize that up, at the meso level, we basically come back to these two interpretations, which I think have more similarities than differences. Either we have these nanocrystalline pockets, which are these kind of granules, which are not joined together, or we have this idea of semi-crystalline regions where sheets can extend from one region to the other. And this is what we're still trying to solve at the time being. But nevertheless, in both cases, we have this big complexity of water in lots of different states. We have water between the layers, we have water absorbed on these little packets, and then we have water in these small pores between these small packets. So that just says the open question there. So just before we have a bit of a break, we'll now come back to something which is more well established, which is what is the microstructure. So now we're moving up again a scale. We're moving up to the micron scale. I say it's well established, but actually it's not quite so well established, because now we have the problem arising from all those different states of water, which is that when we put a sample in the electron microscope, which are these pictures from the electron microscope of different kinds, we've dried the sample out. And we can't be sure that this kind of shape of product we see here is the shape that existed before we took the water away. Now, lots of people have said, oh, we now have these environmental electron microscopes that can solve this problem. And they don't, because if you have water present in an environmental microscope, all you see is the surface of the water. And if you remove that water in order to see what's underneath it, then you've dried it out. Okay? So even pictures in an environmental microscope are not radically different from that. They show these kind of little sea urchin or hedgehog structures, you know, which have some structure of CSH behind them. And, you know, probably the best approach we can get for not drying a sample is this kind of image, which was taken not in an environmental scanning microscope, but in an environmental transmission microscope, where really we could have almost water liquid present. And here you get this idea that we have these kind of films, and these films are really extending into the pore space in this very filamenty way. Now this we're going to come back to, because this is again the problem we have of understanding porosity, understanding water movement. That we don't have a clean division between what's space and what's product. We have an almost continual transition from, you know, this kind of almost one atom plane of CSH going to denser and denser product. And this is what makes understanding concrete, makes the interaction with water, understanding the degradation really so complicated. Putting that aside for one moment, we then can see in the scanning electron microscope two distinct forms of CSH. I showed you earlier, we can see these quite clear rims. So this is a cement grain which has partially reacted. It's quite a big cement grain. And you see here we've got this layer of product around the grain, very, very definite, very dense and quite even. And on the outside of this layer, we've got this very, very small, sort of frizzy outside layer. And you can see that more clearly in this fracture surface here. This is the dense product. These cracks are actually due to the fact we've dried it out to put it in the microscope. And here we have this kind of sea urchin structure on the surface. Now this filmy product, this product like this is the product that's forming first. So this is 3 hours hydration, this is 10 hours hydration, this is the surface of a C3S grain, and you see on the surface of the C3S grain we start to form these little pockets of CSH. They're growing, and then at a later age we form this dense, what we call inner product. Well, why do we call it inner product? Because if you trace this initial outline like this, we think this more or less represents the outline of the original grain. So this dense product here is formed inside the original grain. This filamenty product here is formed outside the original grain. Here's another transmission electron microscope, so we have a higher resolution. And here we can still see the very clear distinction in morphology between this outer and inner product. So here's the outer product. It seems to be this kind of fibrils here. Here's the inner product. It seems to be kind of homogeneous without any particular definite structure. Here's micrographs. Again, we can see the same kind of differences. And even that outer product will fill in over time, but there's still quite clear differences. You see here's an outer product, but it's really filled into a very dense structure, and this is an inner product here. And this will, to a certain extent, I mean, a lot of this is well established, but Eleanor's project will continue to look at these differences, and particularly to look at these differences as they pertain to how the calcium silicate hydrate changes when we put supplementary materials in like fly ash and slag. Finally, I just want to come back to this micrograph and to point out something that's very important, that images are deceptive. So you look at this image, you're a human being, you've been trained over many millennia of evolution to identify features. So immediately your eye is drawn to this feature in the middle, which is a cement grain partially reacted, and then this nice layer around it. And you tend to miss what is actually, in terms of volume, the more important part of the structure, which is all this fine outer product here, which is formed from the hydration of much smaller grains. So, you know, small grains may be a relatively low weight fraction, but they've got a very high surface, and the reaction all happens by dissolution at the surface. So in this final microstructure, the most important part is this outer product here. And you see this has got rather a complex microstructure, you know, with areas of CSH, little pores in it. We don't well understand to what extent those pores are changed by the drying process. You know, if we have this completely wet, is the stuff filling in these small pores? And these are all kind of questions where we want to try and move forward during this project. So hopefully some of you are going to solve some of these unanswered questions. So just to summarize that part of CSH, I think, you know, coming back to it on the atomistic level, we understand fairly well what's going on, although it is a bit complex because we can have these chains being incomplete. We can have aluminium substituting for silicon. The meso level is less clear because really it comes down to the fact, are these nanocrystallites joined together or not? And on the microstructure, we can see these very complex morphologies, particularly of this outer product with these fibrillar or filmy kind of structures. And this is the important part that's formed early through solution. And then this dense inner part, which in terms of transport properties is probably of less concern to us. So we'll take a quick 2-minute break there before we go on to look at everything else that isn't the CSH.